Hello and welcome back to Manifolds, the video series where we talk about generalized surfaces and the integration on them. And one of the most important results in this area is Stokes' theorem on manifolds. And indeed, in today's part 54, we will fill in some more details for the proof of it. In particular, it's quite easy to show Stokes' theorem if we only need one chart. What this means I will tell you soon, because first I want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And as you might already know, as a Steady or Patreon member, you can download a lot of additional material with the link in the description. And now without further ado, let's immediately recall Stokes' theorem on manifolds. Indeed, what we need is a manifold with boundary, and then what we consider are two integrals. On the one hand, we have an integral over the whole manifold M, and on the other hand, we have an integral over the boundary of M. And most importantly, this should happen for an n-1 form omega, where n is the dimension of M. So indeed, this makes d omega a volume form on M. And moreover, omega also needs to have compact support on M. This means, in general, the manifold M does not have to be compact, but then everything interesting for omega has to happen on a compact set anyway. And now please recall, we have already proven Stokes' theorem in the last video for the special case of the half space. And the common notation we have chosen for that was Rn with a less or equal sign in the index. And it simply tells us that we restrict the first component in Rn to be less or equal than 0. Hence, in that sense, the boundary of this manifold is essentially Rn-1. So maybe a quick visualization, here we have our manifold and there the n-1 dimensional boundary. So obviously we can use this fact when we have a chart from the manifold into this half space. And in fact, in this video I want to put the additional assumption that only one chart is needed to describe the whole support of omega. And as usual, we would denote a chart as u, h, where h is a continuous map from u into the half space. So by using the picture from above, here we can find our set u. Therefore, we map this to the half space, and the part of the boundary here is also mapped to the boundary of the half space. So you could say that we simply find a suitable u prime here on the lower level. And as already mentioned, the part of the boundary we have here is now mapped to the lower level as well. Indeed, this is what we already know. This is how a chart with boundary works. And now the additional assumption we want for Stokes' theorem is simply that the whole support of omega lies in this chart u. This means for our integration, we only need one chart, namely UH. Hence with the picture here, inside u, we find our compact set given as support of omega. So the global look of the manifold does not matter, we only need this small part of the whole manifold. And moreover, a small detail we can add here is that the chart should be chosen in such a way that it is orientation preserving. This is the usual thing we want to have for integration, and if we don't have it, it's also not a big problem, because we just have to deal with one sign anyway. So this is the whole assumption we need, and now we can prove Stokes' theorem under this assumption. Which simply means that we have to calculate two integrals and then compare them. Here the first integral over m can be reduced to the integral over u because the support of omega lies in it. So already quite helpful, and now if you want, we can go to the inverse of the chart h, which we usually call the parameterization phi. And this is useful because we can write u as the image of u prime under phi. And seeing the integral written like that, you might recognize the change of variables formula. This means that we can consider the pullback of the differential form and we integrate over u prime. So we just have phi star of d omega, and there you might immediately use the naturality of the exterior derivative. This simply tells us that we can push phi star into the d operation. Hence the result here is that we integrate a differential form over u prime, where we also already know that the support of this differential form lies inside u prime. Therefore, we actually can also write it as an integral over the whole half space. And obviously at this point, we can use Stokes' theorem for the half space. This is what we have used in the last video, and now we can finally use it. So the differential form we have to integrate over the boundary is phi star omega. Or to be actually really precise, it's together with the pullback of the inclusion map I. This simply means that I maps the boundary of the half space into the half space. So this is quite a simple map, but it's needed to describe the differential form here in the correct way. So in the picture you would visualize the boundary on the left and it's included in the half space on the right. And moreover, as before, you also know we can translate everything to the upper level as well. And this works on the right hand side, but also on the left hand side where we only have the boundaries. So there the parameterization phi is restricted, so maybe let's simply call it phi tilde to distinguish it. And in addition, also on this upper level here, we have an inclusion map, which includes the boundary into the whole manifold with boundary. And maybe also this one we can fix as I tilde. And now you should see that this whole picture here commutes, which means going this path here is the same as going that path there. In other words, first I and then phi is the same as first phi tilde and then I tilde. And obviously this also translates to the pullbacks, which means we can do this change here in the integral as well. So more concretely, we have the same integral, but now we write phi tilde star and I tilde star of omega. And now with the same reasoning as before, we don't need to integrate over the whole boundary because we only work in u prime anyway. So the form we integrate will be 0 outside of the boundary in u prime anyway. And by seeing this here, you might recognize the change of variables formula again. This means that phi tilde star is moved to the image here for the domain of the integration. And there's quite clear that this is our part of the boundary on the manifold, so we can go back to an integration on the manifold. And as always, to make it simple, we can just integrate over the whole boundary because of our compact support inside the chart. And that's already it. This is the equality we wanted to show for Stokes' theorem. However, as you already know, usually we will just omit mentioning this inclusion map altogether. Which means there we finally have the formula like we wanted to have it. And the proof of this was actually quite simple because we didn't need to change any charts on the manifold at all. So essentially we just needed the result from the last video to translate it from the lower level to the upper level. But still, this gives us a general result for manifolds with boundary when one chart is enough to describe the whole form omega. If this is not the case, then we actually have to partition the whole form into such single parts we can deal with. And I can already tell you, the keyword for that is partition of unity, and this is what is needed for the general proof of Stokes' theorem. So you see, the rest of the proof will be more work and definitely something for a future video. Therefore, I really hope we meet there again and have a nice day. Bye bye.